Students, today we are going to discuss about polarization of light. All of us know that light waves are electromagnetic waves. So, light waves are electromagnetic waves. So, whenever we say this word electromagnetic, it always says that it will come with electric field and magnetic field. Okay, so they are made out of electric field and magnetic field, and both being perpendicular to each other. So electric field and magnetic field, the orientation is always will be coming with an angle of 90 degree. So if I want to represent the light wave, so it is like this. Okay, so this one is representing the electric field vector, so we will be writing is that E vector. And not only this is we will have the amplitude like this also. Okay, so these are the electric field vectors. And since we know that it also in light wave, electric field will not come alone, it will also be accompanied by magnetic field. So if you want to show it, you will have to show it like this. So I will try to draw it. So it will look like this. So you consider it in a three-dimensional manner. So this is the magnetic field. Okay, so I will call it as B vector. So it is coming out like this. Similarly here also. Okay, so this is the magnetic field. Okay, so what is the issue? So it will get really messy if I consider both electric field and magnetic field to explain the phenomenon of polarization. So it's not like that it is impossible, but yes, to make understand it better, we will explain the now onwards whatever explanation I do regarding polarization of light, I will do considering only the electric field vector. So you should always keep in mind that whenever we are considering electric field vector, there will also be magnetic field vector perpendicular to it, but only for less confusion or to avoid the messy things in the diagram, I am just avoiding it. But same thing happens in case of magnetic field also, if you are going to explain about polarization. Now, so let us go back to the simplest form. So we are going to understand what is polarization. So now I am only considering electric field vector like this. This is electric field vector. My diagram may not be that perfect, so I just, if you try it in your notebooks, it will be far better, I think. So this is the electric field vector. Now for better understanding, we will always be following one axis system, like we call the XYZ axis, like that. So we will be considering something. This axis system we will always consider for reference. Now you can see that if you are watching this, if this is a light wave, okay, and we are considering only the electric field vector, and suppose that you are the observer, okay, and you are seeing this light wave. So for you, the electric field vector is either oriented up or down. Yes, so you can see that in other direction there is no other electric field vector. Okay, so that means the polarized light is that light in which the electric field is oscillating only in one direction. Okay, so it's not necessarily this one. Sometimes you may get a light polarized with electric field polarized in this direction. Sometimes you may get electric field polarized in this direction also. Okay, So this kind of light in which the electric field vector is polarized or oscillating only in one direction, that is called polarized light, and it is simply called linearly polarized because we are considering only one direction. But interestingly what happens, whatever light we have around us, so most of the light around us, say the light from sun, or say light from the bulb that we are using in our day-to-day life, okay, so that bulb that we are using, so all these lights are, most of the light around us are unpolarized. So at the very beginning I told you that the electric field comes with electric field vector, then magnetic field vector perpendicular to each other. Then I said that for simplicity of the explanation I will consider only one component, only one component is the electric field component, and I will not be considering about the magnetic field component. So, but it is not like that, the magnetic field component is not there, it is always be accompanying the electric field vector. Now we saw that in this diagram, that this electric field vector, in this diagram we have seen that for the observer the electric field vector is only oriented along this direction. And then I told you that it is not the case that it will be oriented only along this direction. Say if I call it x, if I call it y, and if I call it as z, so sometime it may be oriented horizontally also, and it may be sometime oriented in this direction, that is the z direction. Now the thing is, so you can see that most of the light, but as I told you that most of the light that are available naturally are not what I can say, they are not polarized, they are unpolarized. So when we say about unpolarized light, so how an unpolarized light looks? So whatever available naturally, how does it look? So unpolarized light, so if you consider again this axis system, okay, so I am considering this x, say y, this is z, okay. So this is again x dash, this is again y dash, this is again z dash, okay. Now as an observer, if you are looking at an unpolarized light, it will have orientation in all the direction, vertical, horizontal and diagonal also, okay. So this kind of light is called unpolarized light, okay. So now the thing is that, first of all, the thing is that let us consider on the fact that how to obtain a polarized light. If you have naturally all the light, most of the light unpolarized, how to obtain a polarized light? So for that we use a polarizer, okay. So it's a kind of for me it looks like a filter, okay. So filter means what? We don't want to want something, so we put it through a filter so that we can get rid of those unwanted things. So the same thing happens with a polarizer. So suppose that you have a bulb, okay, you have the bulb, so light is coming in all the direction like this, okay. So since the light emitted by the bulb is usually unpolarized, so how will it look? It will have orientation in this direction, it will orientation have in this direction, all the direction. So it is clearly an unpolarized light, alright. Now we can introduce the polarizer. So as I said that the polarizer is basically a kind of filter, okay. It is basically made up of a thin plastic, and it is configured in a very special way. So this is not a part of our discussion now, how polarizers are made, but yes, so polarizer, suppose this is a kind of polarizer, so it is having a vertical orientation, so it will let only the vertical components pass, okay. Then you may have another polarizer which allows the only horizontal components, so it's a kind of window, okay. So now suppose that I am putting here a polarizer, and this polarizer allows only vertical component to pass. Okay, my diagram is not that good. I need to draw it in a different way. Okay, so yes, let me draw it like this in a bigger way. Okay, so we have this, kind of slit, or you can say some vertical orientation. So when the light will come out of it, obviously what will happen, the other than the vertical component, other components will be either absorbed or blocked. So what will happen, other components will be either absorbed or blocked. Okay, so for the observer who is observing from this side, for him, he will receive only the vertical component of the light. Okay, so this is called polarized light. Polarized light, and this is the unpolarized light. Okay, so this is a way of production of polarized light. I have already provided a note in a Google Classroom, so all of you can go through it and you can read about polarizers. So, so you can see that here this is oriented in one direction. Again, we ended up with linearly polarized light, right? Now the thing is that yes, I would like to inform you that there are different types of polarizations. Okay, so we are simply now discussing about linear polarization. There will be circular polarization also, so we will discuss it after some time. But before moving on to the next thing, as you have got to know that what is an unpolarized light, what is a polarized light. Now the next step is to talk about why do we care about polarization. So the thing is, why should we care about polarization? What is so important about that? Okay, so most of the we have an experience that suppose you have a water surface, or you are standing near some water surface or some ice or snow or any kind of reflecting surface. Okay, so and obviously you are outside, outdoors, so there is sun shining so brightly, and most of the time we face it that the light is coming. Okay, and when you are standing here and trying to concentrate on something or want to see something, what happens? There will be glare, some kind of glare on your eyes, because of which you are receiving some confusing light. Okay, so or light can come directly to you also. Okay, so in most of the cases we feel so much uncomfortable in our eyes, and we almost get blurred vision and we can't exactly see what is in front of us. So that happens because the sunlight is coming directly to you and it is having different orientation. It is totally unpolarized light and you can't even concentrate on what you are seeing. It will create a lot of confusion. So that means here you see the light is unpolarized, so it will come like this, vertical, horizontal and inclined orientation. So light is coming to you like this, and to you here also it is light is coming like this. Can you see that? Okay, so it just really get you confused what you are seeing actually. Okay, it will give you a blurred vision. Okay, so all of us experience. So you might have seen that in that situation people use sunglasses. Okay, so this is called actually, that is called actually polarizing sunglasses. I will get into that, but let us talk about the natural things. Now here, but in this case you can see that when the light is coming like this, in this case, and here also you can see the light is coming like this. This is vertical, this is horizontal, this is inclined or diagonal orientation. Now when the light will get reflected from this surface, which is maybe water surface, ice surface or snow, anything like that, so then what happens, interestingly, depending upon the orientation of the surface on which the light is getting reflected, this surface on which the light is getting reflected, some of the component will get absorbed. Okay, and only is remaining only see here we have horizontal, vertical and inclined. So maybe one component will get absorbed depending upon the orientation of the surface on from which it is reflected. Maybe two components will be reflected. So finally, so you will get something like this. I am not saying that this will be the exact orientation of the light that you are getting, but yes, mostly this is unpolarized, okay, and it is partially polarized. I cannot say it is completely polarized, but it is partially polarized. And why does it happen? Because it gets reflected from the surface, and the surface will provide some kind of way of removing some of the components, okay. Now, as I said, that when the sun was, shining bright and the light was coming directly to you, okay, and you are trying to absorb, then what happened? Different orientation light is coming like this, okay. So you are getting confused, so you are having some problem in your eye. Then what will happen? Here we can use polarizing sunglasses, okay. In polarizing sunglasses, what happens? Say it will have some vertical orientation like this, okay. That means whenever light falls on it, say it is going with vertical and all different orientation. Say it is going like this, horizontal and inclined, it is going like this. So it will let only, see, the light is going inside your eye, okay, you will receive only the vertical component, alright. So that means then you will have a lot of relief in your eyes, as you are getting a much clearer picture in comparison to the bare eyes or naked eyes. So that means this is a kind of producing, this is a use of polarization. Why should we need a polarizer? And another very interesting use of the polarizer is you might have visited the movie theater where we watch 3D movies, okay. So whenever we watch 3D movies, you might have seen that they give you some special glasses so that you can, without that you can't have the 3D experience. So 3D, again, you know that you see the image in different dimensions, in 3 dimensions you can see. So obviously, if you're let me show you. So here, fine. So obviously, if both your lenses are providing the same orientation, you are going to see the image only in one orientation. You can see only one axis or one kind of image. So you are not going to have a 3D experience. So for that, what you need to do? So if you want to have the 3D experience, obviously you are going to have the glasses. And 3D, what happens? Basically, if you have in one lens, if you have a vertical orientation, another one there will be horizontal orientation. Then only you will be able to see the image in different orientation. Then only you can see the 3D experience, okay. So that is another use of studying polarization and having a polarizer, okay. So that's all about what is a polarization, what is unpolarized light, how to do polarization, and what are the uses of polarization, and where do we see polarization. Now the next thing that we need to be worried about is the types of polarization. Now the last diagram that I have drawn. So simply this is as I said, this is linearly polarized, okay, because you are seeing orientation only in one direction. Now let us here also, you see, this is linearly polarized. This is clearly linearly polarized. Fine. So you can understand here. See here, in case of this polarizer, if I put a polarizer here, okay, and if it is coming with horizontal, okay, orientation, and it allows only horizontal component. So can you see what will be the changes? Can you imagine what are the changes? So changes will be the light, you will receive light only with orientation, this kind of orientation. Okay, so this is also linearly polarized. This is also linearly polarized because electric field is vibrating or oscillating only in one direction. So it may be only x direction, it may be only y direction, it may be only in z direction. Now let us talk about, I hope you are clear about this polarization. Now let us talk about types of polarization. So types of polarization. Okay, so already we have done linearly polarized. Now let me draw one diagram. So here we always have the observer, okay, and you have a light wave, linearly polarized light wave. That's true. Okay. Now this is the electric field vector. Okay. This is the electric field vector, and we can't always consider the amplitude, isn't it? This is a maximum amplitude. Amplitude. We will have to consider these components also, because electric field vector will not always be constant. It will, here suppose it is 0 here, then it is increases here, then become maximum, again decreases and again become 0, again increases, become maximum, again decreases and become 0. So this oscillation it keep on going like that. Okay. Now let me name it as E1 vector. Okay. And now suppose that you are receiving another light. Okay. And that another light is having another polarization. Okay, and that polarization is like this. So don't consider it as a magnetic field component. No, it is another light with another electric field vector. Okay, like this. So let me name it as E2 vector. Okay. So this is E2 vector. Here again it is 0, then it increases, becomes maximum here, decreases, again becomes 0, again increases, again become maximum, then decreases, again becomes 0. Okay, and then again increases and again become maximum. So this way it is oscillating. Okay, so now, so the observer is seeing both of them together. Both these lights are coming together. Both these lights are linearly polarized. But you can see that their orientation is different. If one is in the x-axis, another one is the z-axis or y-axis. They are totally different. Now another thing what I will do, I will introduce a phase difference or a gap of 90 degree between them. Okay, and then I will consider both of them being incident on the observer together. Then what will be the combined picture? Let me draw that. Okay, so the combined picture is going to be very interesting. So you see, this is what the E1. Okay, so it is coming, we need to be very careful while drawing it. Okay, so we need to take care of all the components. This is the amplitude here, then it is decreases, becomes 0, again increases, again. So that's all. Now I will introduce the E2. So okay, this is our E1 vector. Now let me introduce the E2 vector. And since this is a point, this is a point, this is a point, this is a point, so like this, okay, I need to introduce a gap of phase difference of 90 degrees. So how to do that? I will be doing like this. Okay, just okay, so we cannot start from here, you see, because then the gap will be 0 degree. We can't do that. Okay, so we are starting from here. Then you can see that there is simply a phase difference of that much. Okay. Now let us again draw the components. That means the amplitude of the electric field. Like this. It will come up like this. Now what is supposed to, now we need to see, now we need to take care of what this particular person is seeing from his point of view. Okay. Now first of all, let us concentrate on this section. Okay. Now just see that at first, or I can say that, let me draw the axis system. Okay. So at this point you can see that at this point is going to will reach the observer first. This point will reach the observer second. This point will reach the observer third. Okay. So just let us see. So at this point, see what is the E1 vector? Sorry, I need to write. This is E2 vector. Okay. So at this point everyone concentrate. So E1 vector is equal to how much? At this point E1 vector is 0. Okay. And what is the E2 vector? Okay. So resultant is nothing but E2 vector. Okay. So resultant will be in this direction. So if I call it, say if this is the E2, okay, E1 is what? If this is E1, in this direction if we have E1, then it is 0. Okay, so resultant will also be in this direction. Clear? Now next come to this point. Now here what happens? E1 vector is there, but it is not maximum, but okay. Next E2 vector is also there. You see here we have E2 also. So it will be E2. So it will be something. So we need to take the resultant. So we are going to have a resultant. So it will be. So how to do that? This is our E1. Okay, this is our E1. And again we have in this direction we have E2. Okay. So ultimately we will be having the resultant in this direction. Okay. So let me mark the resultant. So first we had the resultant here. Okay. Second we had the resultant here. Now let us go back to this point. Okay. At this point, look at this point. What is that? It is E1 again, and E2 is equal to again 0. So again we are going to have the resultant as E1 in only. So we have E1 in this direction and E2 is equal to 0. Okay. So again we are going to have the, so the resultant is nothing but E2. So you can see that initially at the very first time we had the resultant in this direction. Then in the second step we had the resultant in this direction. In the third step we had the resultant in this direction. So if you keep on doing this thing along this whole direction, then for the observer what he will be seeing? He will be seeing something like this. He will be seeing something like this, like this, like this, like this, like this. Can you understand? So it is like rotating like this. So this kind of light is called circularly polarized light. Okay. So that means if you have two light waves with same amplitude, this thing I forgot to tell you. So E1, modulus of E1 and modulus of E2 should be same. Okay, amplitude should be same, and if there is a phase difference of 90 degree, then the resultant is going to be like this, then like this, then like this. So as a whole the observer will see the light rotating like this. So this kind of things are called circularly polarized light. So similar concept can be applied for elliptically polarized light. So for that, the amplitude for elliptically polarized light, the same theory applies, but there the amplitude are not equal. The amplitude of the two incident light wave will not be equal. Okay, so it will be slightly different. So it will become something like this, say like this, then like this, then like this. So finally, so it will something like this. It will appear like this to the observer. So you can study about the elliptical polarization in the note that I have already provided. So it works in the same way as a circular polarization, only the difference is the difference in the amplitudes. Okay, amplitude of the light wave coming. Okay, so what I told you last about the 3D movies. Okay, so I said that in one thing there will be orientation vertically, and another thing it will be horizontally oriented, so that you can enjoy the movie in different dimensions. So you will receive light in one direction in one eye, in another direction in another eye. But actually this is not the case, because if you do it like this, you will have to keep on tilting your head, okay, to have a better view. Okay, this is not a complete story. Okay, so you will have to keep on rotating or tilting your head to see the picture in a proper way. So it is quite annoying. So you can't have it in a 3D movie. If you want to enjoy, you can't exactly have a glass with orientation like this. So better explanation for this is this. So instead of having a linear polarized light with different orientation in both the eyes, it is, if you have a circularly polarized polarizer which can circularly polarize the light, then you need not tilt your head or rotate your head to have a better view of the 3D movie. So this is actually the glass that is being used for watching the 3D movies in theaters. So this is an application of the polarization of light. There are so many other applications of polarization light. I have already explained in the theory note that I have provided. Please go through it and let me know if you need further discussion. Thank you so much.